Okay, everyone, good evening, or good day, whatever time it is you are watching this recording. You're welcome to another session of our classes, and let's go straight into business. All right, so this is, all right, so once again, you're welcome to the NodeJS intermediate class, and this is brought to you by KodeCamp. At KodeCamp, we're looking at building the skill economy, and this is our 6th class. We've had about 5 sessions, and those 5 sessions have really been power packed. We've looked at quite a good number of things. The first 3 weeks of this program, we've been looking at core concepts. We're looking, first of all, at Node.js, what Node.js is, how it performs, what gives it its biting edge, cut as a technology. And when we looked at it, the asynchronous nature of Node.js, we looked at the event loop in week 1. And from there, we began to look at aspects that Node.js is good at, and we realized that Node.js is pretty good for quite a whole lot of applications. Okay, it's applied in IoT, it's applied in server-side programming. Also for front end, you have React, Vue.js, and different applications. It's also used for streaming. It's very good with streaming. So there's a whole lot of things that can be done using that. As a matter of fact, even NFT projects have been done using Node.js. So you can see that there's a whole lot of application to this. And the next week, we decided to look into object-oriented programming, and we looked at the core concept of object-oriented programming. We looked at the pillars of OOP, talking about abstraction, encapsulation. Then we looked at inheritance and polymorphism. So we looked at this concept in details with practical examples, and the videos are there on YouTube, so you can always go across them. And to start this week, we're looking at the overview of algorithms. In our last class, we talked about what algorithms are, and we saw that, while there could be different steps to which you can achieve an aim, while there could be different steps to which you can achieve an aim, you can achieve a purpose, or you can do some procedure. Some steps may perform better than the other in certain scenarios, and in some cases, some of the steps may not give you the intended results. Like we saw in the last class, we had like a live trial session, and someone came up with a very good algorithm, a very good write-up, and it was pretty great. Okay, it was pretty good. It worked fine for some of the data sets. Okay, so I think about 2 or 3 data sets, it worked very fine. But on a 4th varied data set, that that code didn't work. Okay, so we began to see that there would also be a part of testing. So you want to look at how does your algorithm perform with different data sets, and we considered some key concepts like time complexity, space complexity, and all of that was what we did in our last class. So if you are just joining us, I would advise that if you haven't gone through our last classes, to take some time back to go over the things we've learned, because this is a build-up to what we will be doing in this program in the Node.js intermediate class. So once again, you're welcome to the class. My name is Benjamin Efinudu. I am a seasoned MEN and .NET full stack developer. And I'm going to be looking today at just a few key concepts today, just 2 concepts as we try to wrap all we've been doing over the last 3 weeks, and then begin to look into Node.js itself from a back-end development perspective. Today, we'll be looking at searching and sorting algorithms, and you're going to use them particularly a lot. Okay, you're going to use them particularly a lot. So just look at these algorithms, for simplicity, and to just understand why we work with algorithms. I'm not alone on this. I have here also a mentor, and he is a specialist with Node.js, MongoDB, Express.js, and TypeScript. And you can reach us at on the KodeCamp workspace at Slack. Okay, so you can reach us on Slack at the KodeCamp workspace at Aosoft and at prosper.js. So in the last class, one of the things we looked at is we looked at time complexity, and I wasn't able to show you a pictorial view of what time complexity looks like. So I decided that today's class I was going to start by reviewing the concept, and from there I was going to start by reviewing the concept, and from there we look into what we have for today. So when we talked about time complexity, we described time complexity as the time it takes the program to run. Okay, so simply put, the time it takes the program to run, and we looked at some of those examples. So here we had what we call the big O notation. Okay, the big O notation, and the big O notation is basically just a description of how the time works. And here we have a chart that characterizes the performance. So I'm going to be explaining this concept again, and this time with a chart, so it properly explains what is likely going to happen, the different concepts we use. So let's start with constant time. Now, constant time this is looking up a single element in an array, and that's a constant time operation. Now, when you're looking up a single element in an array, it's a constant time operation because what the element is already stored. Okay, the element is already stored in memory space, and all you're just doing is just trying to access that memory space or that memory location. So looking up a single element is more of a constant time approach, and you see here, regardless of the data set. So basically what we have here is a chart. This is the operation. Okay, this is the operation here. Okay, talking about the operation, and we'll look at it in terms of time. And then here we'll be looking at, or let's say the order of operation. Okay, let's just say order of operation. And here we're looking at this in terms of the size of the data that is provided. Okay, so the data set or the input size, that is what it's being measured against. Now, what we see here is if you have just one data set, all algorithms, okay, will basically work, excellently. So for that work basically excellently. But here you're having constant time starting at this point because yes, it really would take time for it to get it done. So constant time, looking up a single element in an array, yes, it's going to take some time, and regardless of the data set, it's just about you trying to access what the element is. So it's a constant time operation. Now, the next we have is finding an item in a sorted array with a binary search. So today we're going to be looking at binary search, and we'll be looking at the linear search to see the difference between them. Now, in terms of looking for an item in a sorted array, you have more of a logarithmic time, and here we see it as log n. So what it says here is in terms of a small data size, let me bring out a spotlight. So in terms of a small data size, okay, in terms of a small data size, you'd have that as the information or what it is you're looking for is in a small data sample, you have the performance will be a little bit less, okay, to perform worse for searching for something as compared to what we have here, which is a linear time, and we'll see that in practical terms. So generally here, what you see here is you see this curve here. But at this point here, there's a point where it will take relatively about the same time for you to get it. And there's a point where your logarithmic time will do better. Okay, so the binary search over a larger data set is going to do a lot better. But as you see here, you see that linear time needs to shoot up. So this is talking about how expensive this operation will be, or how long it will take for it to give you the result you're looking for. So that's basically what we mean when we see this chart going up here. So the performance of this is over a larger data set poor as compared to this. Okay, so here we've seen this, and one of the key takeaways that I want you to observe here is it says finding an item in a sorted array. Okay, finding an item in a sorted array. Now the next we have is called a linear time, and linear time is as you see here. Okay, the straight is linear, and an example of this is searching an unsorted array for a specific value, and it's more of a linear operation. The next we have is log linear, and this is complex sorting algorithm with heap sort and merge sort. I would like to give heap sort and merge sort to you as more of a take-home assignment. You should do. You should show your code and explain, and we'll give you data sets that you should use in getting this done. Okay, so I'd like to give that to you as an assignment: heap sort, merge sort, and we have here now quadratic time. So you also have the bubble sorts and a selection sort. So these are examples. And how do they perform? Now we see n log n, which is basically this. Okay, so the performance of n log n is more like you've seen the multiplier effect of how this is performing and how this is performing put together, and then you see that when you have a lower, okay, when you have like a smaller data set, you see that the log linear, okay, the log linear has better performance than your than your logarithmic and linear. Okay, so log linear for smaller sample sets has better performance as compared to the linear and the logarithmic time. So this should give you an example of certain case scenarios where one algorithm will do better than the other, and in the long run, it will not do better with larger data sets. Then here you have quadratic time, and this is bubble sort, and here we're having this as, you know, in this range. Okay, so here there isn't x squared, but basically it's just the same as n. Okay, so this is basically just the same as n. This is cubic time, and this is exponential, and this is factorial, and anything from this, they are impractical. So that would be that. That would be that for this explanation. So let's look into some example. So today we're looking at searching. What is searching? Now, searching data and sorting through data, they are fundamental algorithms. Okay, searching refers to iterating. Okay, so you are trying to iterate over the data structures elements to retrieve some data. Now, an example of data structure we looked at last week was arrays. So if you have an array, for example, you want to iterate over the elements in the array to retrieve some data from it. Now, sorting, on the other hand, refers to putting data structures elements, okay, in an order. So in sorting, you might want to put it in order, maybe in order in terms of from greatest to the least, or from least to the greatest. Okay, so that's sorting. You might want to put it in order, maybe alphabetical order. So the searching and sorting algorithms are different for every data structure. So the way you would attend to it in an array may be different from the way you will attend to it in some other data structure, like for example, a hash table. So that's what that part is saying. Now, searching is the task of looking for a specific element inside a data structure. Now, when searching in an array, there are two main techniques depending on whether the array is sorted. And like I mentioned, the key takeaway is sorted. The first is called the linear search. Okay, the linear search. And linear searches are especially flexible because they can be used with both sorted and unsorted data. So you can use linear search for both sorted and unsorted data. However, for binary search, it is more performant, but it works with sorted data. And as a matter of fact, it cannot work with unsorted data. Okay, it cannot work with unsorted data. And I'm going to explain that to you when we get to that. However, linear search has a higher time complexity than binary search. So let's look into the details. So let's start by looking at linear search. Now, how does linear search work? Linear search works by, okay, this is appearing over. Trying to get this, okay, I can get this off. All right, so linear search works by going through each element of the array, from one index after another sequentially. So here you can use different methods for trying to do your search. Okay, you can use different methods for trying to go to your search. You can decide to use a for loop. You can decide to use maybe a filter, a map function, whatever method. It's going to go through each one to get what you want. So here it says what we want to do on this side here. This is we have a data set. Okay, so let's assume this is an array and it has numbers from 1 to 9. Okay, in position 0 to 8. Okay, because this is going to be position 0, 0, 1, 2, and up to 8. So we have numbers 1 to 9. Okay, in this array here, as you can see here, this array. And what we are looking for is we want to iterate through the array. Okay, we want to iterate through the array and check if the number 6 exists in the array. Okay, so this is an example. So looking through this array, what it's going to do is it's going to start at position 1. So starting at position 1, like you're having a normal for loop, it's going to check, is 1 equal to 6? If 1 is equal to 6, return true. Okay, so return true, and then you're exiting the for loop. However, if it's not, then if it's not so, then what you want to do is you want to loop again. So you see here that the loop is still on. So it continues here. It checks number 2. Is it equal to 6? If it's not, continue. 3 is equal to 6, 4, 5. And when it gets to this and it says, okay, we have 6 here, then it's going to return, it's going to return that it's what do you call it? It's going to return this. Okay, it's going to return true that yes, I found this element. Okay, so basically this, what this if statement is just doing here is just to wait for a point where whatever is the element at that index is true. So that's what this is just doing there. So it's going to check, and if it sees 6, then it returns true. And then we are out of this for loop. Okay, so out of this for loop, and we're out of this linear search. So we have that. So for this, we have 6 in the array here, and it's going to return true. Now, looking at the second one, it's looking for 10. And 10, as you can see here, doesn't exist in the array. So here, what it is basically doing here is it's just going through. So this is just like a representation of saying, yes, it's on this array and checking until it finally finds 6. So that's a linear search. So that's a linear search approach. So let's give this a test, and let's give this a test and see. Okay, so let me share my entire window for flexibility. All right, so where is VS Code? All right, so this is VS Code. So let's start with binary search. So this is just basically a simple setup. Just a regular for loop. Just a regular for loop. And if we run this, what's this called? Linear. Okay. So if we run this, it's going to show you true. Okay, so it's going to show you true for this case because we have 6 here, and here we don't have 10 in this array. And basically, if I was to take out 6 from this array, for example, you see both of them will turn out to be, let me just do this. So you see both of them will turn out to be false. So that's just, okay, so that's just by the way, just a simple approach to binary search. Now, let's look at, okay, yeah, so let's look at, sorry, that was linear search. Let's look at binary search, and let's look at the difference between it. Now, in binary search, okay, in binary search, it works on sorted data, and I always like to really specify or clarify that it works only on sorted data. Now, unlike the linear search algorithm, in which every element is checked, binary search can check the middle to see whether the desired value is greater or smaller than it. So, for example, in this sample set, we have about 1, 2, 3, 4, 5, 6, 7, 8, 9. We have about 9 characters, so 5 will be at the middle. So at the middle, it's going to start with 5 and find out. So if, for example, we're looking for 3, it's going to start with 5 and check. Is 5 greater than 3? If 5 is greater than what we are looking for, okay, then it means that we don't have business with this, okay? We don't have business with this other aspect. So instead of you having to go through to check for, the other one, you're going to go 1, 2, 3. Let's look at how many times we went. We're looking for 6, okay? We're looking for 6, and this iteration happens 6 times. 1, 2, 3, 4, 5, 6 for it to happen. But in this case, let's say we're looking for 3. If we're looking for 3, it goes 1, 2, 3, and it takes about 3 iterations to get that done. Here also, it takes about 3 iterations to get this done. So you see at 3, both of them function equally. So let's continue with how it works. Now, it first starts by checking 5, and it asks, is 5 greater than 3? If 5 is greater than 3, then it's going to wipe off this, okay? It's going to wipe off this. All it wants now is it's going to work with this as a new data set. So all of this is discarded, and this becomes the new data set that it wants to work with. Now, in this new data set, it's going to repeat the same process, which is more like recursion. It's going to repeat the same process and check what is in the middle from 1 to 5, and that will be 3. So it checks 3. Is 3 greater or equal to 3? If it is equal to, then it wants to take note of the position, or it depends on what you're looking for. If what you want to take note of is the index, it will let it out to you. Or if what you want to take note of is if it exists in the set, you can also use binary search to do that. So let's look at 7, looking for the number 7. If we're looking for number 7 in linear search, what we would have is we would have to go over this sample set about like 7 times to get the number 7. Okay. Have you guys been seeing my screen since? I hope you've been seeing my screen.
Yeah.
Okay, great. All right. So like I was saying though, it's going to take about 7 iterations for it to get the number 7. But here in the binary search, it's going to first of all start, and the first thing it checks is what is at the middle, 5. Is 5 greater than 7? If 5 is greater than 7, okay, then it's going to take whatever is here, but 5 is obviously not greater than 7, okay? So it means that this is the range in which the number falls in, okay? So the range in which the number falls in is here. Now, remember, this is not iterating over everything one by one, so it doesn't know where 7 is, okay? Right now, this is put in alphabet in order, okay, and they are just separated by like digits of one, okay. But if we had maybe like I'm going to try and change the numbers to have like multiple different numbers, so it doesn't look like you could have just done a for loop to just check that out. So let's continue with this. So now we have 7, okay. So 5 is smaller than this. So every number from here smaller than 5 is wiped off, and then we have this as a new set. Then it starts by checking again between 5 to 9. What is at the middle? Okay, the middle is 7. So is 7 equal to 7, or is it greater than? And here it's equal to 7, and here it stops. So this is happening in roughly about this should be about 2 iterations, 1, 2, and here 1, 2. So I want to give you like a pictorial example of how the two of them work differently. Okay, so here in linear search, what you have is linear search is going to go from one to the other. So it's going to go from one index position to the other until it gets to the number. And here you see it takes about 9 movements for it to get to this. But here, let's look at what we have here in binary search. So in binary search, let me wait for this to start up to see how you can have an idea of the time, right? You can see the idea of the time, how I'm waiting for it to start up. So here, it's done. Second iteration, third, and it's gotten what it needs, okay? So in the fourth one, it's gotten what it needs. So we're going to test, okay? We're going to test the binary search, and we will see how many iterations it takes to get us what we're looking for. So let's just quickly do that. Let's just quickly do that in VS Code. Okay, so, all right, so basically, I have the code set up here already. Okay, so I have the code set up here already, and I'll just run through how it works. Okay, just run through how it works. So here we have function binary search, and it's taking the argument of the array, and it's also taking another argument of the target. So here, this is the array here. Okay, so the array we have, for example, 1 to 4, and what we are looking for, the target value we're looking for is 1. So the algorithm, how it flows through is, as we saw, first is you want to know what is the starting, okay, so what is the starting number? So here, the starting number is going to be 0, and then the ending number, okay, the ending number is going to be the array length minus 1. So the array length minus 1, and this is basically just for index position. So let's say, for example, we have, like an array of elements 1, 2, 3, 4, 5, 6, 7, 8, 9. This is about 9. Okay, so this is about 9 elements in total. So the index position is 0, 1, 2, 3, 4, 5, 6, 7, 8. Okay, so this here now is index position 8. So basically, what this n is just signifying is just the last index. So that's what we mean here by array length minus 1. So let's go over this. Now it says y, and you see here, this is another point where you want to use the while operator. Okay, so here, the while here says while the start, which is 0, is less than or equals to the end. So we did this before by like saying you want to check, you want to check. This is like the point where whatever it is should end. This is like a termination clause. So while the start is less than or equals to the end, because let me show you what I'm talking about. Okay, if you look at the binary search, I have to do this in slideshow form. Okay, if you look at binary search, you see at 7, you see at 8, and then now we see at 9. And at 9 is the point where the start is less than or equals to the end. Okay, the reason why we say less than is there's a chance that what you are looking for is not in the array. Okay, there's a chance that what you're looking for is not there in the array. So if what you're looking for is greater than, all right, then yeah, it should bail out. Okay, so if what you're looking at is not within the context, then it should bail out. So that's the reason why you have that condition there. So let's go on now. So we have let middle be equals to math of floor start plus end. So you're adding the two of them together, and then you're dividing by 2 to know the index position. Remember that this start and end are basically indexes, not the actual values. They are the index position. So the start position plus the end position divided by 2, and you're taking the lower one, that's the math of floor. So that's your middle position. So if what is in the middle here is less than the target, which is what has been specified here. If what is in the middle is less than the target, then at this point, what you want to do is you want to say, let's go over that again now. Let's go over that again. All right. Now, if what is in the middle here, okay, if what is in the middle here is less than the target, okay, what is in the middle here is less than the target, then let's use this. What is in the middle here is less than the target, which is 7, then we don't need all of this, okay? It means the target falls between the middle and the end. What we're looking for, if the middle is less than what we're looking for, then we don't need all of this. So that's what this part is saying. So here it says search the right half. Okay, so you want to search the right half, discarding the left. However, if what you are looking for is if the middle is greater than the target, then search the left half. So it depends on if what you're looking for is either greater, okay, so if what you're looking for is greater, that means it's on the right. If it's less, it's on the left. Then there's also the chance that what you're looking for is equal to the target. So if what you're looking for is equal to the target, then you reply, yes, I have found the target. Okay, so you found the target. So that's how that goes. Then if after all this, okay, if after all this, we have that we didn't get, okay, if after all this, we have that we didn't get what we're looking for, okay, then you want to return -1, which is the standard way of saying not found. Okay, so -1 when searching for something, it's usually a standard way of returning if something was not found. Okay, so let's test this out. Let's test this out and see how that goes. Binary search, and here we have 0, -1, 4, and 1. Okay, so we have 0, -1, 4, and 1, and this is a solution. Okay, so here for 1, this first one, what this is doing here is it is relating the index position at which this should be 0, not 1. Okay, so here it is showing the index position at which a thing was found. Okay, so that's what the result here means, showing the index position at which it was found. Here we're looking at 4, and 4 is not found in this array, so that's why it's returning -1. Here we're looking for 5, and 5 is found at this index position, okay, which is index position 4, and we're looking for 3, and 3 is found at index position 1. And then in a case where you have maybe, for example, you have multiple instances, okay, so let me just put the multiple instances so you see what's going to happen. Okay, so generally here you can see 0, 1, 2, and what is happening basically is that it's overriding. Okay, so it's overriding like saving, it's overriding what has been saved. So just for you to take note of that, okay, so it's just overriding what's been saved, except if what you want to check is if you have multiple instances, then you want to create something like an object. So where it is found, you return where it was found. I think that would be a good way of an assignment. There's an algorithm for that, which is more of an algorithm to return how many, like count, yes, count of certain, like if you have an array appear multiple times, you want to return how many of them you found. There's an algorithm for that. I'll just drop that for you guys later as a good assignment for you to like tax your mind. Okay, so I want to demonstrate here how this algorithm works. Okay, like how efficient it is in terms of the number of times it has to run. So want to do like a comparison between two of them. So what I'll just do is I'll just going to remove, let me comment this out. Okay, so I'll comment this out and going to linear search. I want to also comment this out. Okay, so going to linear search, I want to comment this out. And all right. Okay, so just give me a second. All right, so let's have this up here. Okay, so let's have this up here. In another module. So here I'm going to do linear search. Okay, so linear search. Let me use NodeMon. So change this one. Okay, so NodeMon linear search. Okay, so all right. Okay, so this is returning true. Okay, so this is returning true, and what I want it to do, okay, so what I want it to do is, let's do it this way here. We have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, okay? And for every time this array, okay, for every time this array works, okay, I want to say console.log, okay, I want to say console.log, let me say, let me say time, okay, time, let me say time I, okay, so I'll just call this time I, okay, so for every time this works, I'll just call this time I, and yeah, that should work. And for the binary search here, let me do this with NodeMon as well. Okay, so NodeMon binary search. Okay, so let's see this working. So this is returning 0. And let me see, what do I want to do? So while this, okay, so while this is running, okay, so while this is running, okay, so this is where it's going to look. So what I want to do is I want to I want to create a time. Okay, so I want to create a time, and what I'll just do is I'll just call this let me just call this, let me just say let I, okay, so let I equals to 0, and just let I equals to 0. Okay, so then here I will just say I plus plus. Okay, so I will just say I plus plus for every time I is equal to, let me just say I plus equals 1. Okay, so let me say I plus 1. Okay, just give me a second. I equals to I plus 1. And let me check what's going on. Let me do this here, don't worry. Yes, sorry, please. You said what?
There's an issue on my phone. Check your board.
Your network is not clear. Okay, your network is not clear. Sorry, you said? Oh, okay. I didn't initialize now. Okay, so let me say I plus plus. Okay, and time is equals to I. Okay. All right. Okay, like so. All right. Thank you very much. I didn't notice. I didn't initialize I. All right. So So I want to show you here now is we're going to look at the two of them. This one here, we want to work with the same sample size. So here we have this is going to be okay. So this is going to be the array I'm using here, and I'm looking for 6. Okay, so I'm looking for 6 in this array, and then here also I want to present this array. Okay, here too. I want to present this array here too, and the result here. Okay, the result here doesn't quite matter. The result here doesn't quite matter. Okay, so here I want to look for 6. I want to look for 6 in this array. Okay, so here we look at the time. So this here is let me also add. Let me maybe also add the time because I'm working on different. This is linear. Okay, so let me say linear search time. So that we'll see it here. So we have linear search time. Okay, and in this other one here, we have this other one here. We have binary search time. So let me call this one binary search time. So the concept is going to confuse me with binary search time. Okay, all right. So let's look at the example of the performance. Okay, let's look at the example of performance. Now, in terms of why are the two of them sharing? Like, okay, let me just do one at a time. Let me just do one at a time. I don't know how to them showing this. Okay, so let's look at this. This is binary search. I want to check how many times it's going to perform these iterations to get a result done. Okay, so I'm just going to do node binary. Okay, binary search, and it shows me that it does this iteration. Okay, 3 times, and it gets the results. In 3 times, it gets the results. And then if I was to do that for the linear search now, you see that this happens about 5 times for it to get the results. Okay, so running through 5 times for it to get the results. And if we were to increase the sample size, okay, further to, let's say like a larger sample size and everything, you can imagine now that by linear, you can imagine now that by working with a linear search, you are going to have, okay, you can imagine now that by working with a linear search now, you're going to have an exponentially, or let's say like a constant linear time increase. So it's going to take you that amount of iterations for you to get the result that you want to look for. So let's say we're looking for a number now. Let's say we're looking for 2. Okay, we're looking for number 2. Looking for number 2 in linear search, and looking for number 2 in binary search. So number 2 here in linear search, it does it in 2, in only 2 times. But if I was to do this in binary search now, you see here, it does it in 3 times, which is quite great, like to be able to do it in 3 times. But yes, it does it in 3 times. So here, for very little, when it's early, it will do it well. But if you were trying to go for maybe like a sample size of maybe like 20, which is the last item in binary search, how many times do you need to do that? In binary search, 1, 2, 3, 4, 5 times. Okay, and it finally gets it and the position is there. But if you were to do that same operation in linear search, it's going to run as many times as the last. Okay, so a whole of 19 times. Sorry, I'm still on binary. Okay, now it's going to do that a whole of 19 times for you to get that done. Okay, so what I'm trying to point out to you here is that when it comes to working with algorithms, the purpose of they perform relatively, okay? The way they perform relatively will help you in making better decisions on how you want to work, okay? So here, in this case, we have a constant time operation, which we really didn't do. And then here we have, the binary search, which is working with this operation. So if you look at it now, for larger sample size, as we got to about 20, we didn't really make much increment, okay? We didn't make much increment, just about 5 tries for it to get it right. But when we were dealing with the linear search is based on sample size. Let's look at another aspect just of binary search now. Now in binary search, we have, for example, let's say we have 11, we have 2, we have 13, we have, let's say, 45, we have here 27, we have here 78, and let me delete the rest so that you don't have to go through the stress of this now. Okay, so now this is a good sample, and we are looking for, let me just put in 20. So let me just put in 20. So 20 is 0, 1, 2, 3, 4, 5, 6, that's 6 position, and that's what we're looking for. Now this is for binary search, okay? And let me do the same thing for linear search. So for linear search, I'm going to do just about the same thing here. Is everything right? Okay, code is right. All right. So let's go right again now. So this here is an unsorted data. Okay, this data is not sorted. So we want to go through it, and let's look at this now. So let's do linear search. So linear search, it searches and gets at position 6, which is 0, 1, 2, 3, 4, 5. So at position 6, which is the 6th time, it tells us that this number does exist. Okay, but let's do binary search and let's see how binary search performs. So doing binary search here, we are looking for a number 20. The number exists, but when it looks for what is at the middle, 0, 1, 2, 3, 4, 5, 6, 7, 8. So by 8, the middle will be taken as 0, 1, 2, 3, 4. The middle will be taken as 4. And it says, okay, so at this point here, the middle here should be taken at 45, not 4. It's taken at 45. Now, if the middle is taken at 45, it checks now between 45 and 20. Okay, between 45 and 20, is 45 greater than 20? And it says yes, 45 is it 45? I think it should be this. Okay, let me get this right. Just give me a second. Let me get this right. All right. Here. Okay, so here we're checking for this sample size, and okay, so all right. I just want to get that cleared up. Okay, so checking for this now, it checks to see, like we've seen here, if what is at the middle is less than the target. If what is at the middle is less than the target, which should be, let me 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay, so 45 is what is at the middle. Now, checking for what is at 45, is 45 less than the target? If 45 is less than the target, then it will take this right half. However, 45 is greater than the target. So it is going to now search for what you have here on this left side. Okay, so it's going to search on this side. And searching on this side, it doesn't find it here. So even though we have 20 on this side, it's not going to search here for 20 because it is not, the way the algorithm works is it will first of all check this, and from here know which side to pick. So that's the challenge of binary search. So binary search, as we've seen here, you see it's done the iteration about 4 times, and going through the 4 times, it didn't find 20. Okay, it didn't find 20, and it first went to pick 45 and checked. It discarded this. We now have between 45 and 13, so it picks 13 here. is 13 greater than 20 or less? 13 is less. So it's checking between these two. It picks 4. 4 is less, and 4. Now, if 4 is equals to that, and 4 is not equals to 20, then it terminates and tells you that it's not found. So that's just like the concept of how that works. Okay, so that's just the concept of how that works. So binary search cannot deal with unsorted data. So normally, if you have some operations now, okay, you have some operations now that before you can use them, you have to consider, you have to do a sorting of that information. So if you are receiving a data now and the data is not sorted and you want to do a search in that data, you don't want to go through linear search if the data set that's coming to you is quite large. You don't want to go through linear search. And if the data is not sorted, binary search is not practical. I'm not saying that it is not good. I'm saying it is not practical. You shouldn't use it, okay? So binary search does not work with unsorted data. So at that point, you want to then consider what, in terms of time, would be the cost of sorting the data, okay? So what, in terms of time, would be the cost of sorting the data? So that brings us to a part that we more of like researching, okay? We're going to do more of researching as more like a take-home activity, okay? More of a take-home activity. So that is going to be about sorting. So we have sorting algorithms. So in terms of sorting algorithms, we have something we call the bubble sort. And bubble sort is an algorithm. Let me just put this out here. Let me just put this out here because it's more like a take-home activity. So let me just put this out here so those watching on the screen can get what I'm saying. All right. Let me just duplicate this. All right. So, yeah. So let me just write this bubble sort. Okay. So bubble sort, and let me put this as a bullet point. So we have bubble sort, we have merge sort. I think we also have the quick sort. Yeah, if you have the quick sort. Now the quick sort, the bubble sort, and the merge sort, these are like different types of sorting algorithms. And as much as we will be looking in our next class into the core of Node.js. So in our next class, what we're going to be starting with, we're going to be starting essentially with looking at MongoDB. So our next class is going to be about database, looking at MongoDB. And all these setups, they have their own algorithms, certain algorithms, and some of them are based on some of these operations. So as more of an assignment, you're going to have to take time to study bubble sort and not just study it, but show a code-based representation. Okay, you're going to show a code-based representation. Just the same way I have code here that does what the algorithm requires. That's also the way you also need to like come up with some code, or you can search it up in case you're having difficulty. You can also set up some codes to best show you the algorithm. But the thing is, you need to understand how it works, what each part is doing. Okay. Now, these algorithms, they have their own way they perform. So for instance, in terms of the bubble sort, just like an idea of what the work's going to be like. In terms of bubble sort, the bubble sort is somehow like similar to simple to understand. Basically, what you are doing is that you are looping through the elements, and then when you look through them, what you want to do is you want to like split them into like twos, then check again until you have all the possible smallest possible set of just two elements, like two pairs of elements, and then you want to then check which one is greater than the other. And when you find out which one is greater than the other, we are going to then come back to sorting them and all that. So another concept that I want you guys to have as a take home, okay, is recursion. Okay, I would like to see recursion. So I'm going to be putting up an assignment for the week. I'm going to put up an assignment for the week. It's going to be on this 3 topics. Okay, 3 topics: bubble sort, merge sort, quick sort, and recursion. Okay, and recursion. So you're going to demonstrate them with code, and with that, we'll be wrapping up all we have to do about algorithms and move straight into the work we have for next week. So today, we're not going to do quite much today. We're not going to do quite much today. So what we'll just do is I'll take questions. I'll take questions at this point. Okay, I'll take questions at this point. If there are any questions, I'll take questions at this point. If you have questions, you can put your hands up. Anyone? Questions? If you have questions, whether they are related to today's work or from previous classes, okay, today's work or previous classes, you can ask them. You can ask them today. Anyone? Okay, I have one hand up. Yes, if there's any other person, also put your hand up, okay, so that I can have an idea of how many questions we have here. Okay, so first on here, you can unmute your microphone and ask a question.
Okay, good evening, sir.
Yeah, good evening.
Yeah, I did not quite understand the bubble sorts. You were trying to explain. You said something. You said when there are 2 pairs of data, then to now compare.
The bubble sort. I didn't give like an explanation. If I was going to explain it, I would have put up like slides. Okay, I put up slides for it to explain in detail as I normally do. What I was just saying is just for you to have an idea of what you are searching for. There's going to be your take home, your weekend activity. Okay, so the 4 things I mentioned there: bubble sort, quick sort, merge sort, and recursion. It's going to be your weekend activity. So I wasn't explaining it. I was just giving an idea of what you are going to be looking for. All right. Any other question? All right, you're welcome. Any other question? Okay, so any aspect from the previous classes, any aspect from previous classes or from the assignments that you're giving, any question arising from there? Okay, first on here, you can go ahead again.
Okay, it's about the class we did last week, or was it this week? I think. Yeah, I kind of saw a project. Somebody was sharing a kind of project with me. So the person was using class to control. Actually, it's not really Node.js kind of front end. So the person was using class to control how a page is displaying. Then I was kind of confused looking at the way he was using the method, and I think it was I don't really get some concept about the class.
Okay. But when you talk about that, that was more of a front end work, right? Was it React or what? What was the person working on?
Just normal JavaScript.
Oh, just normal JavaScript in HTML.
Yeah. So
okay.
I don't know how to really explain it. It was something that got me really confused because there were many methods, and they were, like you said last week, parents, is it multiple inheritance or something like that, multi-level inheritance. So I was seeing that in action there, so I really got confused.
Okay. Well, since if I was seeing the code, I would have been able to explain each one bit by bit. But generally, what I would just say is Basically, what the person must have been doing since it's in JavaScript is the person must have had like an event listener that was listening for maybe things like the width of the page. So in front end, they have an event listener for something we call resize. So in case somebody resizes the page, you want to check the size, and then with that, it's more like a conditional statement. Okay, so we will look into when we get into work, we'll be seeing different like conditional statements. Depending on that, you can use switch cases, you can use if else statements, you can use different things. And then in the case where they had the classes, it was taking over the place of the statements. So much of that is not something you need to like bother about. But if you are still having challenges with working with classes, okay, send me a message on Slack so I can share materials that should be helpful to you. Okay, if you are still having challenges working with classes, send me a message on Slack. I'll share materials that can be helpful to you. Then above all, we all need to keep.
Thanks, sir.
Yeah. Okay, you're welcome. So above all, we all need to keep learning and everything. I'm sorry this class for today will not be particularly as long as intended. I'm currently had to like squeeze out so much to be here today, and I just want us to have more of a take-home assignment activities, get them done, send them. Okay, so I'm going to make that available by tomorrow evening. Going to make them available by tomorrow evening. Our mentor is going to post it on the Slack channel. So I would expect that you should have it done by Tuesday next week latest. Okay, Tuesday next week latest. So please look out for that. You already know the assignment. You can go ahead and start doing your search. Those are the 4 things. But I will give a particular example, or rather not example. I'll give a particular like series of tests with which you should test your algorithms. Okay, and see how it performs. So I think that's that for today. In the absence of any questions, I would like to call on our mentor Prosper to address if there's any aspect he wants to address it before we come to the close of today.
Guys, sorry. Yeah. Okay. Thanks, Ben, for the class. And yeah, so guys, I want to address the issue of coming late to the class. Classes start by 7 o'clock, and most of the time, me and Ben were here 10 minutes before the time. So if we can squeeze out time from our schedules and be here 10 minutes before the time, how much more you guys? I know it's different for everybody, and we are all busy, right? But then to try as much as possible to be coming to the classes early, at least 7 on the dot. Everybody should be here, and yeah. So please try and up your game in respect to coming to classes early. And yeah, like I said earlier on this Slack, I'm really impressed with your performances so far. Going over the quiz, I'm seeing a lot of flawless victory scores. Kudos, guys, kudos. So keep it up, and we'll share the tags for this week on algorithms. So just expect and prepare to get your hands dirty as we progress in the course. So yeah, that's much about it from my side. Have a wonderful evening, guys.
All right, so thank you very much, Prosper. So guys, have a wonderful weekend. Next week, we'll be looking into working with MongoDB. So it should be expected that we should learn how to have MongoDB on our local computer. So in case you want to work without using internet for people who work locally, and then we also look at how to work with the cloud MongoDB. So those are two aspects we're going to look at. From there, we look at the basics of cloud operations, and essentially we've moved into like the real serious deal for the week. So next week is a whole lot to do. So I'll see you guys same time, come early next week, Tuesday. See you guys.